J.J. Thomson and his team used all of these experiments to find an important property of these negatively charged particles. They balanced the electric and magnetic field so that the particles went straight through the vacuum, just as we discussed, and this enabled them to calculate the velocity of the particles. When they turned off the electric field, though, the particles were deflected downward along a semicircular path, striking the side of the tube. By observing where the particles struck the tube, which of course caused it to fluoresce, they were able to measure the radius of the semicircular path of these particles as they went through the magnetic field. And this enabled them to determine the ratio of the particle's charge to its mass. A really, really key finding. Let's look at calculating charge to mass ratio. To find the charge to mass ratio, we're going to take advantage of the following. First of all, Newton's second law of motion. Second, the particles have a velocity, which we found was given by the ratio of the magnitude of the E field to the magnitude of the B field. The magnetic field then also provides a centripetal force that moves the particles along a semicircular path when the electric field has been switched off. So here we have Newton's second law. It says here that the net force is equal to mass times acceleration. In this case, the net force is only the magnetic field. The electric field has been switched off. And the acceleration that we see is a centripetal acceleration given by m times v squared over r. If we substitute qvb for the magnetic field, we have this expression, qvb equals mv squared over r. We can rearrange this for q over m, and we find that that is equal to v over b times r. If we then substitute for the velocity, e over b, we'll have that q over m is equal to e over b squared over b squared r. That is, the charge to mass ratio is the ratio of the electric field strength to the magnetic field strength squared times the radius of the path. These measurements resulted in a charge to mass ratio for a cathode ray particle to be 1.76 times 10 to the 11 coulombs per kilogram. Thomson found that this particle had a very low mass for its charge. In fact, its mass per unit charge was 1,800 times less than the previous lowest amount measured for a particle. Before this work, physicists were speculating that the hydrogen atom was the smallest fundamental particle. Well, this result led Thomson to propose that this negatively charged particle was new, and he called them corpuscles. The name electron was taken from George Johnstone Stoney's work in 1874 and proposed again by George Fitzgerald. That was the name that stuck. Furthermore, since the electron was so much lighter than the hydrogen atom, it was concluded that the electron must be part of an atom.